this out, this is equal to positive mz over izz, right? B over 2 plus by my over iyy a over 2. So what we realize comparing these two, right? Stress x at point alpha is not equal to stress x at point y, point beta. So when that's the case, this is where we have what? Unsymmetrical bending. Remember, I told you guys it's all about what? Stress field. Nothing to do with the geometry, nothing to do with the loading condition. It's all based on the what? Stress field, as you can see. So I'm going to do the next two. Okay, so stress x, but what we realize over here, stress x as beta is what? Maximum what? Tensile. Because both of them are what? Positive. Right? If both of them are positive, this shows that it's in what? Maximum what? Tension. Okay, so the next one is stress x at point I. Right? So this is also equal to mz over izz multiplied by y and my over iyy multiplied by z. Okay, so if we look at point y, point I, right? mz, so focus on mz. So mz, I did write mz, is going to be what? Compression, negative. Right? My for point I is also going to be what? Negative. My compression, mz is also in compression. Okay, so when that's the case, this will be equal to minus mz over izz multiplied by b over 2 minus by my over iyy multiplied by a over 2. So for this case, both of them are negative. This is where you have your maximum what? Compression. And then finally, stress x at point J, right? So again, you write mz over izz multiplied by y, my over iyy multiplied by z. Okay, so point J, my is in tension, so this is plus. Mz is in what? Mz, because below the zz line, mz is in compression, negative. So this is equal to minus mz over izz b over 2 plus by my over iyy a over 2. So if you look at all of them, right, we can make this conclusion. For this case, where stress x at alpha will not be equal to stress x at point beta, will not be equal to stress x at point I, and will not be equal to stress x at point J. This is the condition of unsymmetrical bending. Are we clear? This is really, really important. Okay, you have to understand this concept. Are we clear? Okay. As I said, this example I could not show that at all, right? But whenever we calculate the values, none of the values are ever the same, especially at point A and point B. Because point A and point B, if you pick this axis, the left and the right, they share the same what? If you look over here, they share the same geometric distance. Can you see that? Okay, but stresses are not the same. Okay, so that is again a concept of unsymmetrical bending. Okay, right. The last thing that I'm going to do today, just very, very briefly, I know you guys have been hearing my voice for the past over 2 hours. The last thing that we're going to do, okay, is this. The last thing we're going to do is known as eccentric. Symmetrical bending. Okay, I'm aware that you guys have done this in 2P before. I'm really aware. So just to briefly recall, when the term eccentric come in, it means that px is not equal to what? 0. Okay, it means that px is not equal to 0. Okay, and when the term symmetrical comes in, means moment is only applied on one axis. Okay, not two axes. Two axes, you will always get unsymmetrical bending. Okay, so now let's look at a condition. Okay, so this is a very typical condition of unsymmetrical bending. Okay, so this is a condition that where you have unsymmetrical bending. Okay, so you have a structure like this, right? So I'm going to call this structure, this is my X. This is my Y. Over here, this is rotation about Z. Okay, so for this case, okay, failure, okay, for this case, failure will occur at point where? At point C. Okay, point C is where failure will occur. That's where we analyze the C position. Okay, you don't analyze point A, you don't analyze point D, you don't analyze point E, you don't analyze point C, you analyze point C where failure will occur. Later in the course, we are going to do more of this. Okay, we are given a general structure and we have to determine where fracture will occur. Okay, we analyze where the structure will occur, most importantly. Now, the next diagram, which I believe you have seen it before. Okay, so now, right, we split the structure into two, right? We break the structure into two, right? And we focus on where? We focus on point C. Okay. Now, point C will have a reaction. Yes or no? If we look at point C, right? So stress X at point C will be equal. So the P prime is to counter F. Okay. So for this case, we will have, I'll write F over A. Okay. Where F is equal to P prime, okay, due to Newton's what? Third law, which is action equal to reaction, same in magnitude, different in direction. And this is going to induce the axial load. Okay. So based on the transformation we have done, so the bending were, so when we analyze something like this, we basically fix this region. Okay. So this P prime will induce a moment in this direction. See, so when this is the case, using moment vector, this is compression. And this side is what? Tensile. Likewise, over this side, right, it's going to be compression. And this is also what? Tension. The M down here is to react to the P. Okay. So, but what is this? How are we going to calculate moment about the P? Okay. So over here we are going to put minus. Okay, we're going to put minus mz over izz multiplied by y. Okay, where mz is equal to what? So over here, you can see over here, right? This distance from here to here is what we call, they call it the distance, they label it as a distance. Hold on. They call it the distance d. So mz is equal to p prime multiplied by d. Okay, so therefore, stress x at point C is equal to F over A, okay, minus by mz over izz, or no, I will not call it mz. I will call this time now is p prime multiplied by d multiplied by a distance y. Okay, okay. So now I'm going to call, okay, I'm going to call the top part at point C. Okay, I'm going to call the top part alpha. I'm going to call the bottom part beta. Okay, so when we write this, stress x at point C at point alpha is equal to F over A, right? But the top part is in compression, so it's minus P prime D multiplied by Y divided by what? IZZ. Okay? So the next thing that we do is we are going to look at stress X at point C and the at position beta. F over A is still in tension. Okay, F over A is still in tension, but now due to bending, it becomes what? Positive. So it's P prime D Y divided by what? IZZ. Okay. Now I'm going to do something different now. Okay, I'm going to do something different. What if now I'm going to flip it around? What if P prime now? Okay, I'm going to cancel this, right? What if now, right? Our P prime is acting inwards. So all this I'm going to get rid of. Okay. Again, we are going to analyze what is going on at point C. Okay. So now we know that this time this will be acting this way. F will be acting inwards. Right? And then if point C is fixed, the moment due to P is going this way, and action equal to reaction, same in magnitude, different direction. Now this is in compression, and this side is in tensile. The top part is in tensile. The bottom part is in compression. Right? So now when you write this out, okay, based on this situation, stress X, so I'm going to call this point alpha. I'm going to call this point beta. So stress X, point C at point alpha, right? Point alpha. So now the F now is pushing in. So it's under what? Compression. Can you see that? It changed already, right? So now alpha is due to the moment is in tension plus by P prime D multiplied by Y divided by what? IZZ. Okay. So likewise, we have stress X at C at point beta. So this will be, again, the axial load is in what? Compression minus by P prime D multiplied by Y divided by IZZ. Don't memorize the formula. Analyze the structure on how the vectors are acting on. Then you can determine whether it's in tension or in what? Compression. Because if you were to forget one of the formulas where you have minus mz, then you can't remember, oh, it's mz minus or plus, you are in big what? Big trouble. Are we clear? Okay. With that, I'm going to stop now. I will see you guys tomorrow. If you have questions, you can ask me. If not, I'll see you guys tomorrow. Bye.